Yeah, welcome everyone. So our speaker today comes from Oxford. So he's Joseph MacManus. So he's in the final year, I guess, of his PhD, and so he's in the topological group. But his works also concerns some branch of structural graph theory. So it's about more infinite graph. And obtained recently a number of nice results concerning coarse properties of Cayley graphs, especially. And so today we'll present some of these results, I guess. So please.
Great. Well, yeah, thank you very much for the invitation. I must warn you before I start doing any mathematics that I'm a geometric group theorist. I'm not a graph theorist. So I'm probably going to say some heinous things. I'm going to do things like use gamma for a graph and G for a group. I'm probably going to say words that I assume that everyone is born knowing, but you might not have heard. So if at any point I start talking nonsense, just interrupt me, please. But yeah, so this is a talk about asymptotic minors of Cayley graphs. I realise I'm talking to graph theorists, so I will spend a bit of time talking about Cayley graphs. But I will, I've been taking a little bit of time to define what an asymptotic minor is, just so we're on the same page there. So this definition takes ages to write, so forgive me for doing it in advance. But if we let gamma and h be graphs and k be some constant, then we say that gamma has a k-fat h minor if there exists connected subgraphs BV, which are called the branch sets, one for every vertex of h, and paths PE, one for every edge of h, such that if E is an edge, then the path corresponding to E connects the corresponding branch sets. And also we have this second property that says that everything is far apart from each other. So if you are any two of these things, you should be at least K apart from each other infimally, unless you are literally the path connecting that branch set. That's the only time when things are allowed to get close. The idea is that this is like a large-scale copy of H within gamma, and then
So I assume that gamma is considered to be infinite, but in general, do you consider H to be finite, or do you also consider the infinite case?
It doesn't matter if H is finite or not here. Gamma in general will be infinite, so otherwise none of this is very interesting. But now. So if gamma contains a k-fat h minor for all k, then we say that h is an asymptotic minor, and we write this silly symbol here. What I'm particularly interested in is understanding graphs which have some h missing. So let me just add one more word to this. So let's we say gamma is, I'm going to use the phrase asymptotically minor excluded if there exists some finite h such that h is not an asymptotic minor of essentially, this talk is about understanding which Cayley graphs are asymptotically minor excluded. I'll talk about Cayley graphs more later. So, what is the benefit of asymptotic minors? Well, they are wonderful because they don't care about the local geometry. You can mess around with the local geometry, and you can't destroy having an asymptotic minor. So to formalize this, we need an idea of a quasi-isometry. So let me just introduce another definition. So let's let gamma 1 and gamma 2 be graphs. And let me just say now that whenever I consider graphs, I will consider them to be connected. I'm not very interested in disconnected graphs. And I always consider my graphs to have a metric on them, which is the shortest path metric.
Are the graphs weighted?
There's no weights, they're all unit lengths. Yeah, exactly. So let's take two graphs. Let's let and let's consider two constants, lambda, which is at least 1, and epsilon, which is at least 0. We say a map. Let's call it F from gamma 1 to gamma 2 is an I'll write it here, lambda epsilon quasi-isometric embedding if we have the following metric property. So we say that for all, let's say x, y in gamma 1, we have the distance between their images. The distance between their images is bounded above by some linear additive and multiplicative error. So is it most lambda plus delta or d xy plus epsilon? Lambda times the distance between x and y plus epsilon. And we have a similar bound, a similar lower bound, so we say that we have the same thing but with 1 over lambda and the minus epsilon. So essentially, if 2 points in the domain are close together, then they will be close together in the image. If 2 points are far away in the domain, then they'll be far away in the image. So this is what a quasi-isometric embedding represents. And yeah, we say that we also say that F is a quasi-isometry if it's nearly surjective. So this says nothing about surjectivity. We don't want it to be actually surjective. We want it to be nearly surjective. And we quantify this by saying that for all y in the domain, there exists an x, or y in the codomain rather, there exists an x in the domain such that the distance between x, y, and f of x is at most, let's say, epsilon.
So this is again like lambda epsilon quasi-isometric.
Yes, yeah, we should really quantify this. It doesn't matter too much, but we can call that a lambda epsilon quasi-isometry. And yeah, this is an equivalence relation on graphs, connected graphs, in fact metric spaces in general. And so if there exists a quasi-isometry between two spaces, I'm going to write the following notation. I'm going to say gamma 1 twiddle qi gamma 2. Yeah. Are there any questions about this definition? Let me know if my handwriting is ever illegible. Great. So the benefit of quasi-isometries is they quantify this idea of large-scale geometry. So some sort of simple exercises. So proposition. Let's say if gamma 1 and is quasi-isometric to gamma 2, where these are graphs, and we have some asymptotic minor of gamma 1, then we also have the same asymptotic minor of gamma 2. And this is an equivalence relation, so that's actually an if and only if. And this is, if you want something to do, you get bored of listening to me talk, try and prove this. It's not too difficult, it sort of falls out of these definitions. Yeah, and so a simple corollary of this fact is that if, say, gamma 1 is quasi-isometric to gamma 2, and let's say that H is not a minor full stop, is not a minor of gamma 2, then it must be the case that that H is not, H may be a minor of gamma 1, but it can't be an asymptotic minor of gamma 1. So asymptotic minors are somehow an obstruction to having quasi-isometries to graphs which don't have minors. If you have some asymptotic minor, then every graph you are quasi-isometric to will have that minor as well.
So is there a way of, because I'm more comfortable with quasi-isometry than minors.
Okay.
So is there a way of restating the definition of like K-fat minors in like terms of quasi-isometric embeddings? Or if I think it in this way, I'm making some mistake?
That's a good question, and you are making a small mistake. So these minors, you can't. It's an interesting question as to whether you can sort of get these to be in some sense quasi-isometrically embedded, but you can't get this in general. In general, these minors could look ridiculous. They could be incredibly distorted and all over the place and wrap around themselves. The only thing that you have is that you have that you can sort of, no matter how many quasi-isometries you push them through, you can still make out the structure of H. So, yeah, does that help at all?
Yeah.
Okay. Yeah, if there's any more questions, please shout out. But anyway, so on the topic of this corollary, it was the reason that these minors were sort of popularized. It was the following conjecture. Do I have another color? I do. It's the following conjecture. I'm going to write the word false above it. Spoiler alert. The conjecture is essentially that the converse to this corollary holds. So the conjecture is that for all finite H, we have that, and for all, say, for all graphs gamma, we have that H is not an asymptotic minor of gamma if and only if there exists some gamma prime such that gamma is quasi-isometric to gamma prime and H is not a minor of gamma prime. So the question is whether the converse of this holds.
You say not.
Yes. Thank you. So this has been something that people have been thinking about quite a lot recently, and it's interesting to look at where we know something. So it turns out that for many small h, this conjecture is true. Some of them have been known for quite a while. So I have another color. Yellow is a positive color.
Sorry, what's the difference? The conjecture?
The conjecture, so this is an implication, this is a if and only if. So if you're quasi-isometric to some graph which is missing a minor, then you miss that asymptotic minor. The conjecture states that if you are missing an asymptotic minor, you can build a graph that doesn't have that minor full stop and a quasi-isometry.
Okay.
So let's look at some instances as to where this is known. It's known when, there's a lot of names to remember here, but it's been known for a very long time for K3. So this is a theorem of Manning, Jason Manning. It's a theorem from geometric group theory. Follows from something called the bottleneck lemma, which is a nice result. Let me make sure I don't miss any names out now.
So having K3 as an asymptotic minor, that should be a simple condition in just pure graph theory terms. Yes, is it like containing arbitrarily long induced cycle? No.
It's something like this. It's like the idea is that if I take 2 points which are far away from each other, and I draw a geodesic here, and I take a ball around this geodesic, then any path which connects them has to eventually pass through that ball. This is how Manning characterized these. It's called the bottleneck theorem. And there's
So
some.
this is not containing K3.
Yes, this is a characterization of not containing it. So for any two sufficiently far apart points, if you draw a geodesic and draw a large enough ball of radius r, then you end up with this bottleneck.
He didn't do it in these terms, right?
He didn't do it in terms of asymptotic minors. He was more interested in characterizing those graphs which are quasi-isometric to trees. Yeah. So there's a cloth hidden around there somewhere. Yeah. So K3, your positive result due to Manning. For what else do we have? We have I'll just start reeling off examples in no particular order. So K1M, so stars. This is a result of Georgakopoulos and Papasoglu. Fairly recently, this was essentially when this conjecture was popularized, was when they proved this. We have a result of K23 was done in a paper by, there's a lot of names here. Let's see if I can read my own handwriting. Chapoy, Dragon, Newman, Rabinovich, and Baxter. I'm messing up some of those names. And K4 minus, which is K4 minus an edge. This was done by Fujiwara and Papasoglu again. This paper by Fujiwara and Papasoglu was done essentially as an extension of what Manning proved. They were looking for more versions of this bottleneck theorem. And most recently, we have, rather than K4 minus, we have K4, which was done very recently by Albertson, Jacobs, and so these are all the positive results, and maybe there's some other results which I'm missing out, but these are the ones that I've heard of. And there is a negative result which exists, which I don't quite know what the graph is. It's some graph that looks like, I think you have a K15, another K15, and you join them by 3 edges like this, something like this. Then I think this ends up being a counterexample to this conjecture, and this is due to Davis, Hicking, Illingworth, and McCarthy.
Is it not an example for what?
So there exists a graph gamma which does not contain this graph H as a minor, or as an asymptotic minor, but it is not quasi-isometric to any graph that doesn't have this as a minor, full stop. So it's a counterexample to this conjecture. And so it's interesting to ask, well, what is it about this graph which is so special? I don't know, I mean, this is kind of horrible. This is, these all seem like quite nice graphs. And so you can ask a question like, I don't know, I'll take 2 questions which have gained some attention. So maybe I'll give this conjecture a name, call it a star. So I'll say a question, is star true for all planar graphs, all planar H? So all of the examples where it seems to have been verified seem to be really for planar graphs, yeah. So maybe it's true for all planar H. Is it true for grids? We take H to be a grid. This conjecture holds. And then another related question is, if we know that, say, K5 is not an asymptotic minor of gamma, and K3 is not an asymptotic minor of gamma, then is gamma qi to some planar graph, where by qi I mean quasi-isometric. So sort of coarse Kuratowski theorem. So yeah, I mean these are very interesting questions. It seems like every few months a new graph get added to this list. I'm not sure if any more counterexamples have appeared on the other side, but it's something very tempting to understand why we seem to have this divide. The hope was that if this conjecture was true in full generality, then you could essentially push through all of the Robertson-Seymour graph minors project through straight into asymptotic minors and get a billion results for free. It would be very powerful. So the fact that it's failed is a little bit annoying, but trying to understand why it failed.
So this result for this bipartite graph at the top, this is K2 what, 3?
This one up here.
No, the positive result.
The positive result. This is K23.
K3.
Yeah.
So it's even open for outer planar graphs? Is another question?
Yes. Yeah.
So no K4 and no K2.
Well, K4 is known, but for all outer planar graphs.
Yeah.
Yeah.
Are these positive examples like similar in nature, like there is some technique that they sort of push forward, or are they very different?
I must admit I don't know exactly how to prove these, but my impression is that they're all incredibly annoying. I think that because if you want to give a positive example, you need to start with this hypothesis that there's no, there is some k such that I can't find a k fat K4 or something like that, and then I need to build that gamma prime, which has no K4 full stop, and I need to work very hard doing a lot of metric geometry to build quasi-isometry. And it's, I think the techniques are often quite similar, but I think you can't really pull anything from one of them and use it in another one. They're also sort of niche and proprietary. It would be nice to have some more general techniques which work. But, yeah. Right. Any more questions about this before I move on to the next part? Okay, wonderful. So the next thing I want to talk about then is this is a talk about Cayley graphs, as it says here. So I should talk about Cayley graphs. Am I okay to remove this? Really happy with that? This. So now we need to talk about some group theory. I'll try and give examples. So my goal is to motivate the question that I've at least partially solved. Explain to you why it's interesting and explain why it's difficult, and then sort of give an idea of what the tools that go into it are and roughly how they fit together. The end goal of this talk is that there'll be a nice big picture of a Kn minor and a finally presented group later. So fingers crossed we get that. So let's start with. I don't think I started part 1, but we're going to open with part 2 now. We're going to talk about Cayley graphs. So let's just remind ourselves of some things. So let's let G be a group. Sorry about that. Then let's say that I'll put a line here. Let's say that G is finitely generated. If there exists some finite subset S inside of G, which generates G such that G equals this. So if your group theory is a little bit rusty, I mean that any element of G can be made by multiplying together elements of S and their inverses. So G is the smallest subgroup that contains S. Now, given a finitely generated group, I'm going to be lazy, and I'm always going to write F G like this. So given a finitely generated group, and let me also say I'm probably going to forget to call my groups finitely generated at times. So if you ever see a group, it's probably finitely generated unless otherwise stated. So if we have a finitely generated group, we define a graph gamma, which is, depends on G and S, depends on a choice of generating set, as follows. So what do we have? We have the vertex set of gamma. It's just my group, and we have and the edge set is going to be well, let's think of it this way. We're going to have an edge connecting every element of G with GS, where so G is in G and S is subgenerator. So yeah, so we join edges together if I can get from one to the other by just multiplying on the right by some generator.
So this is a directed graph, or you consider this as undirected?
That's a very good point. I'm going to consider it as an undirected graph. Really, this graph comes with directions and also labels. So this edge would be labeled by S. But as far as I'm concerned, I only care about the coarse geometry of this graph. I don't really care about the labels. So I'm going to forget all of that and just think of it as a connected, unweighted, unlabeled graph. Now, I'll give some examples of this in a second, but there's a little bit of a sort of work I should do to get there. Here's the reason why I'm so interested in quasi-isometries. So exercise, this really is an exercise. If you haven't done it before, you should do it. It's good for you, good for the soul. So if, say, S1 and S2 are two finite generating sets of G, then the Cayley graphs are quasi-isometric. So while the Cayley graph depends on some choice of generating set, it kind of doesn't in a way, because while all of these Cayley graphs might look a bit different, they're all basically the same. And so we have this well-defined equivalence class of metric spaces, which we can prescribe to any finitely generated group in some canonical way, which is the equivalence class, the quasi-isometry class of its Cayley graphs. So this means that it makes sense. To write something like H is an asymptotic minor of a group G, where this is a graph and this is a finitely generated group. So, a priori this looks like nonsense, but when I write this, I really mean this is an asymptotic minor of some, and hence any Cayley graph of G. Right. So now, now the next thing I want to do is give another exercise or so. So another exercise which is worth doing to move to geometric group theory. Let's say that G1 is a subgroup of G2, and these are all finitely generated. And let's say that G1 has finite index in G2, which means that there are only finitely many cosets, if you remember your group theory. Then this means that G1 is quasi-isometric to G2. So finite index subgroups basically have the same geometry. This is worth doing. And another exercise which is kind of nice to note is that if...
Sorry, so this that G1 is quasi-isometric to G2, you now mean that you are taking any Cayley graph of G1 and any Cayley graph of G2, and they will be quasi-isometric.
Yes, exactly, yeah. So it's... I'm going to talk in a very hand-wavy sense about quasi-isometries between groups, because all of the Cayley graphs are quasi-isometric, and whenever I say this, I mean just take any Cayley graph and it will work.
Okay, so in this case, you assume both G1 and G2 to be finitely generated?
Yes.
Just enough to assume that G2 is, and then it follows that G1 is?
Yeah, it's so one is finitely generated if only if the other one is. So you can assume that G2 is finitely generated, for example. So now another example, which exercise which I will give is that if G1 is a subgroup of G2, and in this case I want both to be finitely generated, I need to take this. Then if we have some asymptotic minor of G1, then we can push this through and see an asymptotic minor in G2. This is another good exercise to do. It follows from the fact that if I have an inclusion of groups like this, then I get a map between their Cayley graphs, which is not quite a quasi-isometric embedding, but it's something called a coarse embedding, which is a bit weaker and is still enough to have this monotonicity of asymptotic minors. So I won't say too much about coarse embeddings because the definition's a bit fiddly and there's only so many hours in a day, and I'm not going to use it again. But yeah. So before I give some examples of Cayley graphs, I will need to do a bit of legwork talking about group presentations, because we need to talk about finitely presented groups. So let's just jump straight into this. So I'll try and give the most combinatorial definition I know. So definition, let's let x say equal to x1, x2. So this is an alphabet. I'm going to write x plus or minus to be the set of, well, that's right. It's going to be x union the set of formal inverses. So I'm also going to now include the symbols x1 inverse, x2 inverse. Now I'm going to define x star to be the set of words over the x plus or minus. So finite words. Now let's let R be some collection of words, any collection of words. And now I'm going to define a set. I'm going to define a set x. I'm going to write it like this. And it's going to be defined as simply x star modulo a certain equivalence relation. And this equivalence relation is going to be the relation between words. So it's where, let's say, W1 is related to W2. And if, let's say like this, W1 can be transformed into W2 what I want to say is inserting or deleting elements of this R. So take one word, and I'm allowed to take elements of R, and I can sort of insert them somewhere in W1, or if I find one, I can take it out. So inserting or deleting subwords from R. And I have to add another caveat, which is that if I ever see xi inverse or something like this, I'm allowed to delete that because this is just a trivial relation. I'm also allowed to add that in freely if I so want. Using words, I'll say all trivial relators. So we have this. We take two words. We have these sets of defining relations, and we use this to define an equivalence relation on the set of words. And now this is a group, right? This is a group by concatenation, where I so let me write this here. I say that X R is a group via the operation. If I take two equivalence classes of words, then their product is just defined to be the equivalence class of their concatenation. So this is a group. And in particular, any group can be defined in this way, as isomorphism. So this is a sort of combinatorial model of four groups. It's an idea due to Walter von Dieck from like 1882 or something like this. Very old definition. But does this make sense right now? Any questions, comments, concerns? Wonderful. So let me. So now this is an idea of a group presentation. And I'm just going to, I'll write this here. I'm going to say that a group G is finitely presented if G is isomorphic to some presentation of this form, where X and R are both finite. So this is different to being finitely generated. Whenever I have finitely presented, I'm going to write FP rather than FG. But there are groups which are finitely generated but not finitely presented. So for example, the lamplighter group is the sort of classic example.
The other way?
The other way, as in groups which are finitely. Well, if you're finitely presented, that's a good question actually. If you're finitely presented, then you're automatically finitely generated because X will give you a generating set. It's not immediately obvious, I suppose. So anyway, let's look at some examples. So examples. So for example, Z, the integers, has a sort of nice presentation where we take a single letter and we take the empty set of relations. And now if I think about the Cayley graph of Z, which corresponds to this generating set, we just wonderfully get a finite line. If I take Z squared, this has a presentation of this form. So by this I mean Z cross Z, so the Cartesian product of groups. This has a presentation of the form where we have one relator. We do this. This defines Z squared. And if I take this generating set, which somehow corresponds to the standard basis vectors in Z squared, then we get a grid like this. And more, if I take Z cubed and I do a similar presentation, I'll get a three-dimensional grid. Z4, I get a four-dimensional grid. You can define these groups in a similar way. Now, one example I would like to do more explicitly is a group. I'll write it here. BS1, 2. So this is a group which some of you may have heard of. It's defined in the following way. So we have two generators, A, B, and we have one relation which is AB, A squared, A to the minus 2, B. So we have, it looks a little bit like this, but that minus 1 there can replace with a minus 2. Now the Cayley graph of this is kind of interesting because what it essentially looks like is like a Cartesian product of trees, of a tree with a line, I should say. So take a free regular tree, give it a sort of dominant direction, and then take a Cartesian product with a line, so sort of in this direction like this. You can imagine subdividing this. Another leaf like this. This will look something like this. And so the Cayley graph sort of looks a bit like this geometrically, where as you move up or down this tree, depending on your point of view, we sort of these bricks get a bit thicker, as it were. So up here, on this layer, we're going to have something like this. But if you were to sort of glue disks in like this, you would just get topologically a cell complex, which is a product of a tree with a line. The reason I want to bring up this example is that this example is important because it's easy to see that it is not asymptotically minor excluded. So we can sort of immediately build big minors here if we want. So how can we do this? Well, I might take, maybe I'll do it like this. Let's suppose I wanted to build a K4 or something like this. And I wanted it to be, if I wanted to build a sort of a big K4 in this Cayley graph, what I could do is I could imagine taking everything on this line here, this line here, this line here, and this line here, and this could be these lines could be my branch sets. And then my paths joining, maybe I take my first path to be something that goes like this. And then maybe my second path is something which is moved somewhere down here, but maybe it goes somewhere like this, and then it comes up and gets that, but further down the tree. And then the next one might be somewhere down here, and it goes all the way down here, and then comes along, and then comes up and goes up to there. And sort of using this kind of trick, I can kind of cheat and build a large copy of K4 or any Kn. And if I want it to be more fat, I can just sort of push this further up the tree, and it will spread things out. And so this is a sort of first easy example of a group which is not asymptotically minor excluded. Does this picture make sense? It's a tricky Cayley graph to draw, but I think I've managed to get away with it. So now we're sort of ready to state our main conjecture.
So just one question, like kind of seems like not a regular graph here, but this is just a matter of picture, yes? So like when you branch one way, you do it every second vertex, and you branch another way every second vertex.
Exactly, yeah. So
and
like
the other second vertex. Yeah.
So there will be a square which is like this on the other side, which joins those two together. So yeah, each sheet sort of looks like a brick wall which is progressively subdividing, and then those where it subdivides, it sort of breaks into two sheets.
So you actually don't have this tree which is written on the left.
This tree.
It's like in the structure, but
that's a good point. The
yes.
tree is secretly not there. Yeah, the tree is a figment of my imagination. There is some sense in which the tree is there topologically, but you need to sort of imagine there being disks filling in these squares. This is also a tree that the group actually acts on this tree, so it's kind of there in terms of the symmetries. But that's a bit out of scope. Any more questions? So let's get ready to do this main question. So I'll need another definition. So let's define the definition. So this is just some terminology to make my life a bit easier. I'll say we call a finitely generated group. I'm going to call it quasi-planar. If there exists let's call this G. If there exists some planar graph gamma such that G is quasi-symmetric to gamma. So any group that satisfies this is certainly not going to be is going to be asymptotically minor excluded because it's QI to a planar graph, so it can't contain a fat K5, for example. Z squared is a quasi-planar group. Z is certainly quasi-planar. It's QI to the real line. There are lots of other examples, but there's not that many. So the structure of these groups is fairly restricted. Let me just state a quick theorem to explain why I mean these don't really appear. So this is a theorem of myself from 2 years ago now. I'm getting old. It turns out that a group, finitely generated group G, is quasi-planar if and only if there exists some G prime within G, a finite index, such that G prime commits a planar Cayley graph. So one direction of this is straightforward. If we have a finite index subgroup which has a planar Cayley graph, then of course my big group G is going to be quasi-symmetric to that planar Cayley graph. The converse is not obvious at all, but it's sort of worth noting that this completely restricts what these can be because the planar Cayley graphs, the groups that have those, are incredibly well understood. There's only so many that exist. They're completely characterized by Georgakopoulos and Papasoglu. And they're all virtually, they all basically have, how do I say this? There's certain words I'm not allowed to say right now, so if you don't know what they are, that's okay, but they're all virtually free products of free and surface groups. And there's only so many of those. Right.
Is there any motivation to have a Cayley graph planar? Is it like some weird condition to state, or is there some meaning to it?
Well, if you have a Cayley graph which is planar and is also free connected, so it's not disconnected by any cut pair, then it follows from a theorem of Whitney that you can extend the action on the Cayley graph to an action on a planar surface. And then once you have a group happening on a surface, rather than just its own Cayley graph, this is geometrically like a very strong thing to have. You can really deduce a lot of algebra by just looking at the action on the surface. So this is like somehow this was the first example of geometric group theory that existed in the world. Was Max Dane in 1910-ish studied groups which act on the hyperbolic plane, and he was the first person to realize that actually having that kind of geometry acting on the surface is actually a really helpful thing to have. So this is why we care about planar Cayley graphs in some sense. Any more questions?
Did you need your finitely presented assumption?
Here, no. That's what makes this actually so difficult to prove. So I don't assume finitely presented. It follows a posteriori that this is indeed finitely presented, but the assumption is here we don't need that there.
And so you can say it as quasi-planar is the same as virtually planar.
Yes, exactly. That's not obvious. I shouldn't say that's my theorem. That's okay. Anyway, I'm here to talk about a conjecture, and that conjecture is the following. So we had this false conjecture, which I got rid of before, that said that a group is a graph rather is has no h asymptotic minor if and only if you have some gamma prime which are quasi-asymmetric, which has no h minor. This is this turns out to be false in general, but a very strong version of it is conjectured to hold for Cayley graphs. So the conjecture is that a finitely generated group G is asymptotically minor excluded if and only if it is quasi-planar or virtually planar, as we say. So as soon as if you look at your Cayley graph and you say, I can't find a K1 billion in there, it turns out there's actually not even a K5. This is quite a strong conjecture, but somehow it's the idea is that that minors are everywhere in Cayley graphs. They should be at least. It's a fun conjecture to have. I quite enjoy it. Does it make sense? Are we convinced that it's interesting? You don't have to say yes to that. Anyway. So now, for the next 25 minutes or so, I want to motivate how to prove this. Before that, I will need to talk a little bit about splittings and ends of groups. I will try and make that brief and also make sense. So here's a quick crash course. I'll write that on the board. So crash course on ends and splittings. Right. So how do I want to do this? So let's take let me motivate what a splitting is. Maybe I'll do it in a certain way. So I'll do it this way. Let's let G be a group, and let's suppose that G, right like this. G acts on T, which is a tree. So we have a group action on some simplicial tree, a graph theoretical tree. Now I'm going to assume that there is no, so I'll write it like this, so with no global fixed point. So somehow this really is an interesting action on this tree. There's no fixed point which is being fixed globally. And then let's let E be some edge in this tree. I should also say actually that I'm going to wave my hands at this, but without inversions. So I also want the action to be without inversions, which just means that if I have a group element which fixes an edge stepwise, then it fixes it pointwise. So there's no edge and no group element which like flips that edge over. I just want to avoid that because it makes everything a mess. But it's not really important. So with this definition, let's let E be an edge of my tree, and let's let C be a subgroup of G, which is exactly the stabilizer of E. So it's the set of elements. I'll write the definition. It's the set of elements G and G such that G E. So I look at the stabilizer of this. And then the terminology that I want to introduce is I say that we say that G splits over C. This is just terminology. Now, as graph theorists, this might seem like a silly definition, which doesn't seem very helpful, but I promise you that you have really secretly seen this before, because what this really means is this is essentially the same as having a canonical tree decomposition of your Cayley graph. That's all it really is, where the tree is T, and what we essentially have are these, so we essentially have a tree decomposition of our Cayley graph like this. In the structure of this tree, where the bags, the bags are basically the vertex stabilizers, and the edges, the adhesion sets, are essentially the edge stabilizers. So we're taking a tree decomposition of our group, an algebraic tree decomposition, and it basically corresponds to a tree decomposition of the Cayley graph. And this idea is something, if you want to read about it, the keyword is Bass theory. So I know that a lot of you have thought about tree decompositions before. When I started thinking about graphs, I had to spend some time reading about tree decompositions, and yeah, it turns out it's just Bass theory, as you said. And so maybe you'll find the other way helpful to think about. Bass theory is just tree decompositions. But I'm interested in, I want to be able to talk about splitting over groups. So when I talk about splitting over a group, I essentially mean that there's a tree decomposition where my subgroup is an adhesion set. Right. Now I need to talk a little bit about ends. So let me go here. So let me motivate quickly what ends are. So let's let gamma be a Cayley graph. This could just be a graph, preferably connected locally finite, but this could just be any graph. But I'm going to take it to be a Cayley graph. Let's say that two simple rays. So I mean, subgraphs isomorphic to the sort of half of a real line. Say R1 and R2 gamma. We're going to say that these are end equivalent if for all finite subgraphs, let's say F inside of gamma, we have that R1 and R2 are eventually in the same component of gamma minus. So let's draw a picture. So maybe this is what gamma looks like. This is my gamma, and maybe this is my finite. Maybe this is some finite subgraph F. Then if I had maybe these three rays, this is R1, this is R2, maybe this is R3. This finite subgraph F is kind of witnessing the fact that R3 is different, is not equivalent to R1 or R2 because it's being separated by this finite subgraph. But based on this picture, it could be the case that R2 and R1 are equivalent. So this is an equivalent relation on the set of rays. So let's say the equivalence classes are called ends. And an end is essentially a direction in which you can move towards infinity. And I'm going to write E of G to denote the number of ends of gamma. Now, this is a bit of an abusive notation. I've written E of G when it's really a property of gamma, but the ends of the locally finite graph are Qi invariant, so this makes perfect sense to say. Any questions about this? Wonderful. So, just very quickly to state one theorem which sort of clarifies why we care about these. So, proposition, let's let G be finitely generated, then one of the following has to happen. So, we could have that E of G is 0, in which case G is finite. And we could have that E of G is equal to 1, in which case you can't really say anything. This is somehow the most general situation to be in. This means that there's no finite subgraph which separates your thing into infinite pieces. We could have E of G which is equal to 2, so you could have two ends, so two directions to go to infinity, in which case this is the same as saying that G contains a copy of Z, and this copy has finite index. It's also equivalent to saying that G is quasi-asymmetric to the real numbers. And finally, the other general case that can happen is that E of G could be infinite, in which case it's a fairly deep result, but this is equivalent-ish to saying that G splits over a finite subgroup. So remember the definition of splitting. This is a theorem of J.R. Stallings. So anyway, this is ends, this is splittings. Kind of the reason I really wanted to get to this is that we need to be able to talk about splittings, and we need to be able to talk about two-ended subgroups, so subgroups which have two ends which are quasi-asymmetric to the real line. Are there any questions right now? Okay, wonderful. Well, what I want to do now then for the last 20 minutes is I would like to talk about a specific instance of this theorem that we're going to prove.
So, a question about item 4.
Yeah.
I don't understand if the tree is, for example, the path, then it looks like you have only two.
Yes, yeah. This is kind of, this if and only if should really be like both of these.
Okay.
Yeah, kind of secret. Just this case is kind of degenerate. Yeah, if your tree is a path and it has finite stabilizers, then you have your two-ended, but you do technically split over a finite subgroup. So good catch. I was wondering if anyone would notice that. It's kind of a fiddly detail that I hate talking about. So remember, the conjecture now is that our group, the conjecture is that our finitely generated group is asymptotically minor included if and only if it is quasi-planar. Now we are going to prove, well, we're going to sort of see roughly why this is true for finitely presented groups. It is wide open for non-finitely presented groups, but I want to sort of sketch roughly why this is true for finitely presented groups. I'll do the most interesting case. So let's call it theorem A and 24. The conjecture, so a finitely presented group is asymptotically minor excluded. Let's write this. If and only if it is quasi-planar. Right, QP. And yeah, the proof of this really uses a lot of properties of finitely presented groups, which are not true in general. So if you want to drop this finite presentability condition, you're going to need a completely different idea. But let's start just walking through how to do this. So I'm going to prove it. So I'm going to assume in the sketch that G does not split over a finite or two-ended subgroup. So there's no splitting of my group, no action on a tree where the edge stabilizers are finite or even two-ended virtually Z. Why I can do this is, I mean, there's a big question mark there, and I don't have time to go into all of the details, but somehow this is the most general state to be in. If you split over a finite group, you can kind of just, forget about that and just think about one-ended groups. It kind of doesn't really make a difference. This is also not obvious. This requires accessibility. If you split over a two-ended subgroup, turns out this gives you quite a lot of geometry, and there's enough known about splitting the finitely presented groups where you can essentially reduce to the case where it does not split. So I'm going to make this assumption. And this is the most general case to be in, because here I'm essentially saying that imagine we had some helpful geometry that was going on that would give us a clearer picture of our group. But we're just saying that doesn't exist. We're saying that actually we don't have any helpful stuff going on, which makes this a bit of a pain, because now we're dealing with the most general types of finitely presented groups. So now the trick to proving this is we need a theorem. I will vaguely motivate this theorem. So let's let gamma be a Cayley graph of G. Given some subgraph Y, we say a component of gamma minus Y is what's called deep. if it contains points arbitrarily far from y. So I take some subgraph of gamma, call it y. I remove it. I look at the remaining components. Some of these components might be rubbish. I'm only interested in the deep ones. And now the definition I want to introduce is we say that some subgraph Z coarsely separates gamma if there exists some, say, R goes from 0, such that the R neighborhood of gamma, well, I'll define that in a second, but we want the complement of the R neighborhood of gamma contains at least 2 components. And so this R neighborhood, I'm just talking about the set of points x and gamma such that the distance from x to z is r. So this is what it means for a space to coarsely, a subset to coarsely separate my graph. And now so now I want to just state a theorem. This is a big theorem. Big news at the time. But that's so one more definition. So a quasi-line is I'm gonna wave my hands a little bit and say coarse embedding is a coarse embedding of R into gamma. So by coarse embedding, it's a weaker condition than being a quasi-isometric embedding. It just means it's somehow uniformly proper. And now the theorem that I want to state is the theorem of Papasoglu, which is essentially where we're going to find some geometry that states that if some polyline of let's say in gamma that coarsely separates, then G splits over a two-rounded subgroup. So this is a
Your assumption on gamma?
I see. So here, that's a good question. So gamma is a Cayley graph of G, where G is finitely presented and one-ended. That's a good point. So if we have a splitting over a two-ended subgroup, it's not too hard to see from the fact that it's comes from like a tree decomposition that subgroup is like a separating quasi-line. Papasoglu showed the converse, that if you have a groups, I'm missing a hypothesis here. Actually, we need to be very careful and say that G is not quasi-planar as a counterexample otherwise. Panos showed that the converse is essentially true, apart from some silly edge case if you're quasi-planar. If you find some separating line, then it turns out that you can use that to actually find an action on a tree and get a splitting over a two-ended subgroup. And so what we get then is, because we're assuming that we do not split over a two-ended subgroup, this means that we get the negation of this. And it turns out that this is helpful for building minors. So yeah, I think I'll write it here now. Does that make sense? Does the theorem statement make sense? Wonderful. So now I'm going to just get started and try and draw a big picture. Some bits you will have to sort of take for granted, but I think it's a fun argument. So now let's prove this. Let's prove this theorem for groups that don't split over small subgroups using Papasoglu's theorem. So let's do a sketch. I'm showing my 2 steps over here. So firstly, I'm going to fix let's start by letting n be some constant greater than 1 and k greater than 1. And I'm going to build a kn, a k-fat kn minor. So the first step in this construction is I'm going to fix a bi-infinite geodesic gamma naught in my Cayley graph gamma. So this is going to be, let's draw a picture of it, maybe it looks something like this. So here's my bi-infinite geodesic. Now next I'm going to choose, so now I'm going to choose some constant r, which is, it's much bigger than n squared k, let's say. It's some huge constant r. And I'm going to consider the R neighborhood like this. And I'm going to subdivide it. I'm going to subdivide into say n choose 2 layers. So here is my large neighborhood. I'm going to just, so let's do the case where n equals 3. I'm going to sort of split it into 3 layers, like this. So I've got sort of a tube around gamma naught, and then a bigger tube, and then a bigger tube. Now, the complement. So the complement, if I look at the complement of this R neighborhood, by Papasoglu's theorem, by Panos, we know that there is only one interesting deep component of that complement. Everything else is nonsense. So, so I can sort of imagine the deep complementary component sort of hanging around up here. So this is the deep component. And what I'm going to do is I'm going to drop from this deep component. I'm going to take a sort of a selection of points like this, which are far apart, and I'm going to drop down geodesics onto this line. I'm going to consider some geodesics like this. Drop them down. And so there's how many of these there are there? There are n of them. So, say drop down n. I'm going to call them hosts. So there's 1, 2, 3. Now, this is a bit which you'll have to take on a little bit of faith. It follows from the fact that I'm finitely presented, that if I take, say, a point here, which is in the middle of this, and a point here in the middle of this, then I can build a path which goes from here to here, which is a sort of constant height. So, if you can imagine that there is a path which sort of maybe it sort of wraps around gamma naught in some interesting way, but it's not too difficult to use finite presentability to build a path such that this distance is fairly constant up to some bounded perturbations. And so that's the next step. I'm going to build what I call constant height paths. So I'm going to build one for every, and choose two heights here. So I'm going to build one for every path. Maybe I'll have a path here. Maybe I have a path here. And now, what I would like to say naively is that here is my Kn. The branch sets are these vertical posts, and the paths are these yellow paths that I've built. This is what you'd like to say. But you can see what the problem is here. Maybe I have some my K neighborhood of this branch set, something like this. Maybe this crashes into it in some ways. And that's a bit of a problem. And so what I would like to do now is I would like to fix that. So let's draw a ball around this. Just do a sort of point there and draw a ball around it like this. And say, okay, well, what I would like to find now is I would like there to be a path from here to here through the ball, which avoids this pillar. I want to avoid that. So I want there to exist a path like this. And maybe it doesn't. Maybe it doesn't exist. I say, okay, well, that's a shame. I tried to do this, it didn't work. Maybe my constants weren't big enough. And so what I'm going to do now is I'm going to draw a picture over here. I'm going to remember this. I'm going to say, okay, well, what did I have before? I had a geodesic segment like this. I had a ball around it. That's a neighborhood. And I had a point here and a point here, such that these really couldn't get past this. This segment separated that ball in that annoying way. And I'm going to remember that. Let's call this row 1. And now I increase my constants. I increase R in particular, and I do this all again. I play the same game. This K neighborhood, this is like K across. This doesn't increase, but the size of this ball does increase. And I do the same game again. And I say, okay, well, can I find this path now through that ball which avoids the post? If it doesn't work again, come back here. I say, well, now I found something like this. I found a bigger one. Right, now it's like a bigger ball. And some path like that, which seems to have separated it. And as I increase my constants again, because it didn't work, I do the same thing again. I find a even bigger ball like this. And this seems to be separated from this. And I continue doing this, getting arbitrarily big, and either this goes on forever, or I'm done, and my construction works. And now the trick is that if this goes on forever, I can use my group action to say, let's take the midpoint of all of these balls. I can assume that they are the same base point. I can assume these are all some fixed vertex of these balls. So these are all balls based around the same point. And so let's call these geodesic segments row 2, row 3. Now it is an application of let's say this. So by the Ascoli theorem. By the Ascoli theorem, these row ends will converge to some infinite geodesic. After passing to a subsequence. So say without loss of generality. So the Ascoli theorem says that these are going to converge uniformly on compact sets to something, and that thing will necessarily be a bi-infinite geodesic. And the fact that I have, at each scale, I see that I'm separating a bigger and bigger ball in this kind of uniform way. I see that this limiting I see that it must follow that rho coarsely separates so the limit of these geodesics has to coarsely separate my Cayley graph, because we sort of have bigger and bigger separation properties at every point. And that's a contradiction, right? This contradicts Papasoglu, because this implies that I have a quasi-line which coarsely separates, which means that my group splits, but I assume that it doesn't split. So contradiction, I'm now very happy. At some point when I was increasing my constants, I was playing this game over and over again. At some point, this path must exist, and I can build my minor in peace and make these little corrections. And so I see a nice picture of a Kn. Now, just in the last minute, so this proves that this theorem holds for groups which don't split. As I say, this is somehow the most general case. If you want to prove it for all finitely presented groups, you essentially then have like essentially a decision tree where you say either your group splits, in which case you do something, or it doesn't split, and you're done. Now, if it does split, you have a few cases, and in all of these cases, either you conclude by some means, or you find some one-ended finitely presented subgroup, and you pass to that subgroup and you play with that subgroup instead. And then you sort of you iterate this process along this decision tree, and either you eventually terminate and find all your minors because of something like this, or this decision tree goes on forever. In which case you're done for different reasons, and that's actually the easiest case to deal with. I don't have time to explain how that works, but I will stop there. I think I'm